This is molten steel. When it cools, it will solidify and grains will be formed. Let's find out what the grain structure of a piece of plain carbon steel is like. We've given this piece of steel a mirror-like finish. Now we're etching it. The steel contains 0.4% carbon. So far, so good, but with the unaided eye, we can't see any grains. We'll have to take a small sample of the steel and view its surface through a microscope. Here it is, magnified nearly 250 times. Let's take a closer look at this in a diagram. In the case of steel, there are two different types of grain. We'll look at each in turn. The light grains, like this one, are made up of iron. Engineers call them ferrite. These give steel the property of ductility. The other grains, like this one, are made up in layers. The white layers are iron. The black layers are a chemical compound of iron and carbon, called iron carbide. Pearlite is the name given to this type of grain. They give steel the properties of hardness and strength. This particular piece of steel is made up of roughly equal numbers of the two types of grain. So far, we've only looked at 0.4% carbon steel. However, steel can be produced with other carbon contents. What effect does this have on the grain structure? We'll start with 0.4% carbon, and let's add some more. Can you see what's happening? The number of pearlite grains is increasing. Now there are no ferrite grains at all. The steel now contains 0.8% carbon. Under the microscope, a similar piece of steel looks like this. You can probably guess what will happen if we now reduce the amount of carbon in the steel. The number of pearlite grains decreases, leaving a lot of ferrite grains. Now there's only about 0.1% carbon left. This is what a similar piece of carbon steel looks like under the microscope. Now we can change the mechanical properties of plain carbon steel by a carefully controlled sequence of heating and cooling by heat treatment. Let's find out what effect heat treatment has on the grain structure of the steel. The rings we're treating contain 0.8% carbon, so all the grains are of the same type, pearlite. Nothing happens until the temperature reaches about 720 degrees centigrade. Now at the grain boundaries, new grains begin to grow. These new grains are quite different to the original ones, and they grow until they completely take over the old structure. Here we're normalizing, so the components are taken out of the furnace and left to cool in air. Let's see what happens to the grain structure. As the temperature reaches about 720 degrees centigrade, the old type of grains begin to reappear. These grow until they meet their neighbors. This structure appears to be very similar to the one we started with. But if we compare the two, we find we've reduced the size of the grains and made them more uniform. We've also changed the properties of the steel. Here's a similar piece of untreated steel. Let's see how tough it is. Remember, toughness is its resistance to shock loading or impact. about 60 units. The broken surface reveals a very coarse grain structure. Now we'll test another piece of the same steel that's been heated to a high temperature and left to cool in air. About 100 units. It's much tougher. This time the broken surface reveals a much finer grain structure. In another form of heat treatment, plain carbon steel is heated to a high temperature and is then cooled rapidly or quenched in water. This treatment increases the hardness of the steel. Let's find out what it does to the grain structure. We're going to heat up a piece of 0.8% carbon steel to 750 degrees centigrade. Remember, with this particular amount of carbon, we have only one type of grain. Nothing happens until the temperature reaches about 720 degrees. Now, exactly the same thing happens here as it did in normalizing. New grains of a completely different structure grow out at the old grain boundaries. Right, now for the quench. As the temperature falls, in each new grain, a needle-like structure forms. This structure is very hard indeed. It's also brittle. We can relieve the brittleness by tempering. In this case, we're going to temper at about 500 degrees centigrade. Tempering modifies the structure of the needles. Inside each needle, small flakes of carbon begin to appear. Now the steel is much less brittle, but it's still harder than it was before heating and quenching. So far, we've only looked at the heat treatment of 0.8% carbon steel. What happens if we try to harden steel containing 0.1% carbon? Here, the grains are mainly iron. Again, nothing happens until the temperature reaches about 720 degrees centigrade. And once again, the new grains begin to form until they completely take over the old grain structure. In this case, we have to take the temperature up much higher to nearly 900 degrees centigrade. If we quench it now, there's insufficient carbon for the hard, needle-like structure to form. We've finished up exactly as we started.